Welcome to my channel, Department of Chemistry. Today we will continue our last topic, that is spin-lattice relaxation. In the last video, I explained to you what is spin-lattice relaxation, and today I will tell you what is the effect of temperature on spin-lattice relaxation. Before I will proceed ahead, I will little review my previous video so that you will understand this video very well. In the last video, I have told you that the mechanism of spin-lattice relaxation is known as nuclear dipolar interactions. As you know, mechanism of nuclear spin-lattice relaxation is known as nuclear dipolar interactions. Okay, that you know because I have already explained it in my previous video. As we know, our sample whose NMR we want to do, suppose I have a sample here. It is in the sample tube. This sample contains millions of molecules. Okay, suppose this is a sample whose NMR we want to do. As we know, this sample contains millions of molecules, and these millions of molecules contain millions of magnetic nuclei. Okay, and these millions of magnetic nuclei are associated with the millions of magnetic moments. Okay, when we expose this sample to external magnetic field, suppose this is the external magnetic field B0. Okay, when we expose this sample to the external magnetic field, as per the Maxwell, we know as per the Maxwell's, the molecules never be in the rest. They are not in the rest. They are continuously in the random motion. Some are moving in one direction and some are moving in the different direction. Okay, so as we same logic we will apply here. This is the sample in the sample tube. Similarly, as per the Maxwell's, these molecules definitely cannot be in the rest. Some molecules are in some direction, some molecules are in the another direction. When molecules are in different directions, their magnetic moment is not a unique. They will modify its magnetic moment. For example, suppose this is our external magnetic field. When some molecules whose magnetic moment is in the direction of external magnetic field, in that time what happens? This sample magnetic moments feel more field because the field has been increased, because the field which is associated with the nucleus is in the same direction with the external magnetic field. Okay, now in any instant of time, some magnetic moments are in the opposite direction of external magnetic field. In that time, what happens? The field strength has been decreased and sample will observe less field. Okay, so we call that sometimes field will increase, sometimes field will decrease. So when sometimes field will increase, when sometimes field will decrease, and it will give rise and fluctuating magnetic field. Okay, now the nutshell statement is over that due to the random motion of molecules, the sample will give rise and fluctuating magnetic field. This magnetic field will fluctuate definitely at some frequency. They will increase or decrease. This increase decrease should be at some frequency. Okay, we call this frequency as an X frequency. Okay, so we call this frequency as an X frequency at which the sample is fluctuating, giving the fluctuating magnetic field. Now, as per the nuclear dipole interaction says that when the fluctuating magnetic field fluctuates at a frequency equal to the resonance frequency, we call that time that these two magnetic fields, these two frequencies are in phase. When they are in the phase, what happens that time? Suppose I have two energy levels. This is an alpha energy level, okay, and this is another energy level, that is beta energy level. Some nuclear spins are in the beta energy state and some nuclear spins are in the alpha energy state. When this fluctuating magnetic field frequency matches with the resonance frequency, that time we call this resonance frequency and this magnetic field frequency are in phase. When they are in phase, what happens that time? The spin state in higher energy state relaxes into the lower energy state, and the excess energy which is associated with this spin has gone into the lattice. Lattice means the solvent in which we have dissolved our sample. Okay, so we call this mechanism is known as we call this relaxation process a spin-lattice relaxation, because this spin state has to be relaxed into the lower energy state and the energy has to be gone into the lattice. So we call this is an spin-lattice relaxation process. Okay, this I have already explained in my previous video, but today's our topic is different, that is dependence of spin-lattice relaxation on time. Now, if this spin state will spend a large time in the excited state and will not relax sooner in the lower energy state and will not impart its energy to the lattice, that means this spin state will spend a large time in the excited state. That means its rate of energy transfer from spin state to lattice is less. Okay, that we call this time the time required by the spin state to relax from higher energy state to lower energy state is known as spin lattice relaxation time. Okay, again I will repeat, you try to understand what I am telling. This spin state, suppose this is a higher energy spin state, this is an lower energy spin state. How much time this spin state will require to impart its energy to the lattice, okay, and itself gone into the lower energy state? How much time the whole process will require? This is known as spin lattice relaxation time. Okay, suppose if the now there are two cases. If the spin state will spend a large time in the excited state, that means it will not easily impart its energy to the lattice. That means it will take time to relax from higher energy state to lower energy state. That means we call this situation has a large spin lattice relaxation time. Okay, now if the spin state is such that it will relax faster into the lower energy state and the energy transfer is faster, that means it will take less time to relax from higher energy state to lower energy state, that we call that this situation has less spin lattice relaxation time. So okay, in the nutshell, you remember, if spin state will spend a large time in excited state, it has larger spin lattice relaxation time. If it spends less time in the excited state, then its spin lattice relaxation time is less. Okay, so when its spin lattice relaxation time is less, it is self understood that it will impart energy to the lattice faster. Okay, now I have written this line. What I am telling to you, the time constant for the rate of energy transfer from the magnetic spin to the lattice is known as spin lattice relaxation time. Okay, getting? Now I will tell you dependence of spin lattice relaxation on the temperature. Now you try to, this is a simple concept and you need not have a big chemistry to know so that you will understand this mechanism. This is a simple concept. You keep mind conscious towards me and you will, inshallah, you will understand this topic very well. Suppose if the temperature, if we have a sample tube in which this is a sample tube, okay, in which there is a sample. If we keep the temperature high, okay, then if we keep the temperature high, what will happen? Molecules will rotate fast. In the nuclear dipolar terminology, we call the rotation tumble. We did not call rotation, we call rotation is another word of tumble. Okay, Tumbling means rotation. Okay, we call that, now I will tell in place of rotation, tumble. If we keep the temperature very high, the molecules will tumble very fast. When they tumble very fast, the fluctuating magnetic field due to the tumbling will achieve the resonance frequency faster. Okay, similarly it is a logic, because faster the motion, faster they will achieve the resonance frequency. When they achieve the faster resonance frequency, okay, then what happens, because I have already told you, when the fluctuating magnetic field achieves the resonance frequency, in that instant energy has been transferred to the lattice and spin has to be gone into the lower energy state. When it achieves the resonance frequency faster, that means it will spend less time in the excited state. When it spends less time in excited state, that is the rate of energy transfer from the higher energy state to lower energy state will be the faster. Okay, will be the faster. Okay, when it is the energy transfer is the faster, okay, that means the spin lattice relaxation time is less. Okay, getting? I have written this line. When temperature is low, okay, this is another term. When temperature is low, the molecule tumble means rotate slowly. They will rotate slowly. Okay, and less is the probability it matches the resonance frequency. That means resonance frequency of magnetic field is not of sample is not achieved sooner. Okay, and therefore slower is the rate of energy transfer. When there is a slow rate of energy transfer, that means spin state will spend large time in the excited state. Okay, that means larger is T1. T1 means spin lattice relaxation time. We represent the spin lattice relaxation time by T1. Okay, and vice versa. And when temperature is high, the molecules will achieve resonance frequency fast. When they achieve the resonance frequency fast, the rate of energy transfer is fast, and spin has to be relaxed fast in the lower energy state, and the spin lattice relaxation time is less. Okay, as we know, then this is all about the spin lattice relaxation time. Now, what is the effect of time on the width of spectral line? That I am going to discuss with you. As we know from the lifetime broadening, delta E into delta T is nearly equal to h divided by 2 pi. This is the Heisenberg uncertainty relation. The Heisenberg uncertainty relation is this one. Delta x into delta P is nearly equal to h divided by 2 pi. H divided by 2 pi. Okay. I have derived this relation from this relation. If you don't know about this relation, you can consult any book or watch my video where I have derived this equation from this equation. Okay. Now we are interested in this equation. We will discuss this one. This is delta E into delta T is nearly equal to the h divided by 2 pi. Okay. Now try to understand this one. This delta E, what is this delta E? What is this delta T? Suppose we have a two energy status in the hydrogen nucleus. This is an alpha energy state and this is an beta energy state. Okay. How much frequency a nuclear spin will absorb and it will go from alpha state to beta state, that is equal to what is the energy of this state, E2, what is the energy of this state, that is E1, and the difference of these two, that is E2 minus E1, is equal to the h nu. That means that amount of this frequency. As we know, this nu is equal to the E2 minus E1 divided by h. As we know, this E2 minus E1 is equal to the nu is equal to delta E divided by h. Okay, that means this is delta E. Okay, that means how much frequency has been absorbed from absorbed, so that the spin state from this state will go from this state to this state. It is equal to the nu is equal to the delta E divided by H. Okay, that means we have to shine the sample that much of frequency, then the spin state will go from this state to this state. Okay, this is delta E. Now, as for the Heisenberg uncertainty, it states that we cannot calculate exactly this delta E value. There is some uncertainty. Uncertainty means if this delta E has a value, for example, if this delta E has a value 10 kilojoules, okay. As per the Heisenberg uncertainty, it states that there is some uncertainty of plus minus delta E. That means there is an uncertainty of plus minus delta E. That means suppose this delta E has a value of 5 kilojoules okay, per mole, and this delta E is 10 kilojoule per mole. Okay. So as per the Heisenberg, now this energy state, the difference between the two energy state we cannot calculate by it is exactly equal to delta E divided by H. It is as per the Heisenberg, there is some uncertainty of delta E. For example, if delta E is 10 kilojoules, this delta E is plus minus 5. That means delta E can be 15, or it can be 15, or it can be 5. That means this delta E, what is the energy difference between the two energy states, can have value from 5 to 15. Okay. Now, how much frequency our sample will absorb? How much frequency our sample can absorb? It is 5 to 15 kilojoule, for example, divided by H. Okay, that means there is a range of energy. If we giving the value 5 minus 15, there comes one value divided by H, the one energy value comes. Okay, if we give all the if we solve this one, this is 5 plus 15 divided by H, or the energy difference can be 5 plus 5 minus 15 divided by H. That means when we start to shine the frequency, a range of frequencies from 5 plus 15 kilojoules divided by H to 5 minus 15 kilojoule divided by H. That means a range of frequencies has been absorbed from this to this. Okay, this is about the Heisenberg. This is about the Heisenberg uncertainty principle, what Heisenberg is telling. I will repeat this one because I think that you have not understood this concept well. I will repeat this one again. You try to understand. Suppose, as per the Heisenberg, it states that delta E into delta T is nearly equal to the H divided by 2 pi. Okay. This delta E is uncertainty in the energy. I have wrote here where delta E is the uncertainty in the energy, and delta T1 is the lifetime of excited state. That means this delta E is uncertainty in energy, this delta T is the lifetime of excited state, and the multiplication of these two quantities should have equal to this constant. If one quantity will increase, this quantity definitely should have to decrease, so that the multiplication will become the constant. If this will decrease, this has to be increased, so that the multiplication will be the constant. Now, you try to understand. Suppose these are two energy levels. This is alpha and this is beta. How much energy will spin state will absorb to go from this state to this state? It is equal to what is the energy of this state, what is the energy of this one, and difference of these two that is E2 minus E1 is equal to the delta E. Okay, this delta E is equal to the h nu, and nu is the frequency. That means nu is equal to delta E divided by h. When we shine that amount of frequency to our sample, then there is a transition from this state to this state. Okay, getting? Now, as per the what is this delta E? This delta E is one quantity, this delta E is another quantity. This delta is the energy difference between the two energy states. This delta E is the uncertainty in energy. What is this uncertainty? That I am trying to explain you. As per the Heisenberg, its state is that we cannot exactly calculate this delta E amount because there is some uncertainty. As per the Heisenberg, its state is that this delta E can have error from plus minus delta E. That means, suppose if the delta E has a value 10 kilojoules and this delta E has a value of suppose 5 kilojoules. Okay, that means if the energy difference between these have 10 kilojoules, we have calculated theoretically, but there is some error of, for example, it can be 10 plus 5, 15 kilojoules, or it can be 10 minus 5, only 5 kilojoules. Or that is, the frequency that sample can absorb is equal to the nu is equal to delta this 10 plus 5 divided by h to 10 minus 5 divided by h. That means this frequency can absorb from this value to this value. That means a range of frequencies from this value to this value has been absorbed. When the range of frequency will be absorbed, for example, that means range of frequencies has been absorbed. That means we will not get a sharp peak, we get a broad peak like this. Okay, because range, there is an uncertainty, range of uncertainties. Okay, this is the meaning of this relation, what I am telling you. Now you try to understand. If you have not understood this one, please watch my Heisenberg uncertainty principle video. You will understand well it there. Now try to understand. This is delta E to delta T is nearly h divided by 2 pi. We will apply this relation to the Heisenberg's uncertainty, in the spin-lattice relaxation process. As you remember, this delta is uncertainty energy and delta T is the uncertainty in the lifetime. Now, you keep mind here, if the temperature is high, that means delta T spin-lattice relaxation time should be small, because higher temperature, faster will the molecules will attain the lower frequency, and they faster will go into the lower energy state, and is delta T1 should be the small. Okay, when this delta T1 becomes small, then this delta E should have to become large, because as I have already told you that the multiplication of these two quantities should be equal to the h divided by 2 pi. When this quantity is small, this definitely has to become large. When this becomes large, that means their uncertainty become large. That I have wrote here only for sake of understanding 5. It can be more than 5, it can be less than 5. That means this uncertainty can be large. When uncertainty can be large, that means the range of frequency, large number of frequency has been absorbed. When the large number of frequencies has been absorbed, what happens at that time? We get a large broadening. That means we get a broad peak, not a sharp peak. Broadening of spectral line due to spin-lattice relaxation. Okay. Now, if the temperature is low, if temperature is very, very low, delta T is large. This is a common. When temperature is low, molecule will not achieve resonance frequency faster. When they will not achieve the resonance frequency faster, that means they will spend a large time in the excited state. When they spend a large time in the excited state, then this delta T become large. When this delta T become large, this delta T should have to become small. From the above relation, this delta E has to become small. When delta E becomes small, less broadening, because when delta E becomes small, that means this uncertainty, we are going towards the exact value of delta E. We are not moving towards the uncertainty. There is a less uncertainty. That means less number of frequencies has been absorbed, and we get a sharp peak. So I have written here that means less broadening of spectral line due to the spin-lattice relaxation process. Okay. So from these above fundamental lines, we write here width W means width of spectral line is inversely proportional to the T1. T1 means spin-lattice relaxation time. If the spin-lattice relaxation time is large, okay, that means if time is large, width is small. That means spectral line is sharp. If spin-lattice relaxation T1 is small, okay, if it is small, then width is large. That we get a broad peak. Okay, you write this. What I have written, width of spin, so width due to spin-lattice relaxation process is inversely proportional to the spin-lattice relaxation time. Okay. Now, what is the outcome of this topic? What is the, if we pose a question to you, suppose we want a sharp peak. How we get a sharp peak? Can you tell me the answer? How we get a sharp peak? There is a logic. Simple fundamental. If we want to get a sharp peak of a sample, then what we have to do? We have to decrease the temperature. When we decrease the temperature, what happens? Spin state will spend a large time in the excited state, and it is spin-lattice relaxation time become large. When time becomes large, delta E, uncertain in the energy, becomes small. When it becomes small, and the less number of frequencies has been absorbed, and we get a sharp peak. Definitely. So we have to keep the temperature of our sample at liquid nitrogen or liquid helium. I have written this line. In order to get a sharp peak, we should have to increase delta T1. How we will increase? Which can be achieved? The temperature of the sample should be lower to the liquid nitrogen or liquid helium. Okay, definitely. Now there is a concept. We have two types of samples. One is solid sample, okay, one is liquid sample. In the solid samples, molecules are tightly held, okay. They will not achieve resonance frequency faster because molecules will not tumble faster, okay. They will not achieve easily the resonance frequency. When they will not achieve the resonance frequency easily, what happens? They will spend large time in the excited state. When they spend large time in the excited state, what happens? Their spin-lattice relaxation time becomes large and large. Okay, when it becomes large and large, then their uncertainty, this delta E quantity becomes small. When it becomes very, very small, that means we get a sharp peak. So we call that solids will give sharp peak. But in place of liquids, if we have a liquid sample, what happens there? Molecules are not tightly bound. They are loosely held. When they are loosely held, they will achieve resonance frequency easily and faster. And they will spend less time in the higher energy state and go on to the lower energy state very fast. And spin-lattice relaxation time becomes very, very less. When it becomes less, that means this quantity becomes less. Then this quantity has definitely to increase. When it increases, then uncertain energy becomes large, and large range of frequencies, large number of frequencies has been absorbed, and we get a broad peak. So I have wrote here. This is solid sample. It is spin-lattice relaxation time is large, and this is the liquid. It is spin-lattice relaxation time is less than the solids. When it is spin-lattice relaxation time is large, it will give sharp signal, and when it is spin-lattice relaxation time is large, it will give broad signal. So in the NMR, solid samples give sharp signals, whereas the liquid samples give broad signals. This is all about the spin-lattice relaxation process. If you have any confusion in this topic, please watch first video, mechanism of spin-lattice relaxation, video 1, then go to this. You can understand this topic then when you watch my first video. But there is a problem in my first video. This year quality is not good. You can maintain the quality by in settings your mobile. You keep the HD quality, and you will get what I am telling. You will inshallah achieve. You will understand this video well. Now this is all about the spin-lattice relaxation process. In the next video, I will explain to you what is mechanism of spin relaxation. What is spin relaxation, and what is the mechanism of spin relaxation. Okay, thank you.